In this video, we are going to learn how to compute the derivative directly by our knowledge of one variable calculus. This will be facilitated by the notion of directional derivatives and partial derivatives. So as usual, the setting is f is from u to r, u is subset of Rn, open. We are in this setting. Suppose we know that f is differentiable. F is differentiable at this particular point x in u. Okay, now fix a vector, fix v in Rn and fix this vector to be a non-zero vector. Fix a non-zero vector. Then we know that we can do f of x plus tv minus f of x, and this will be equal to dfx tv plus e of tv. This equation will be valid whenever t greater than 0 is suitably small. Okay, in fact this will also work when t is less than 0 and is suitably small. Okay, all you are saying is that the vector tv is sufficiently small that x plus tv is in the domain of x plus tv is in the domain of u. Okay, now we divide by t on both sides. So what you get is f of x plus tv minus f of x by t is equal to dfx v plus e of tv by t. Note, I have gotten rid of that t. This t I have gotten rid of. That's because dfx tv is just t times dfx v, because dfx is a linear transformation. It's a linear functional. Now observe that as t goes to 0, e of tv by t goes to 0. Well, to see this, all you have to do is you just have to multiply and divide by norm v. Okay, so as t goes to 0, this will go to 0. Of course, you might object that there should actually be a modulus of t here, but that really doesn't matter. That's just going to change the sign. And as we are claiming that this term goes to 0, it really doesn't matter whether there's a plus t or a minus t in the denominator. Okay, so writing e of tv by t as e of tv norm v divided by t norm v, we see that this term e of tv by t goes to 0 as t goes to 0. What is the net upshot? Well, the net upshot is the following. It's that limit t going to 0, f of x plus tv minus f of x by t, this is equal to dfx v. Okay, now intuitively what this expression f of x plus tv minus f of x by t limit t going to 0, what this gives the rate of change. So this is the rate of change of f at x in the direction or along v. Okay, so essentially what we are doing is we are just considering a line passing through this point x along the direction v. That's what this x plus tv is supposed to denote, and we are restricting f to that line. So f in some sense becomes a one variable function, and we are differentiating f in the usual sense. That's what this is doing, and the net thing that you get, limit t going to 0, will measure the rate of change in that particular direction. The new thing that we have got is the fact that if f is differentiable at the point x, this is in fact equal to dfx v. So the derivative linear functional dfx allows you to compute the rate of change in each direction. Okay, so we formally make this into a definition now. Definition. So let v not equal to 0 be a vector in Rn, vector in Rn, we define the directional derivative of f along v at x to be the limit t going to 0 f of x plus tv minus f of x divided by t. Of course, provided the limit exists. Okay. So, as I have said, we will consider v not equal to 0. Okay. Now, for what do you say? For notational convenience, oh, by the way, I didn't introduce the notation. This directional derivative is denoted by dv of f of x. Okay, directional derivative of f at x along v is denoted dv f of x. Okay, so for notational convenience, we define d0 f of x to be just 0. So the directional derivative along 0 is defined to be 0 just by convention. It's a formal definition. Okay. In particular, if v is ei, that is one of the standard basis vectors, we define the ith partial derivative di. We don't put the ei for convenience. Di of f of x is just, as you can guess, f of limit at t going to 0 f of x plus tei minus f of x by t. Okay, so the ith partial derivative is actually nothing but dei of f of x. Okay, so this is a specific case of the directional derivative. Okay, now I am going to assume that you have already studied basic multivariable calculus in your first year of BSc, or whichever course, BTech, or whichever course you are taking. I am going to assume that you have already studied taking partial derivatives and directional derivatives. Now, other commonly used notations for the partial derivatives include things like del f by del x I, okay, or in the case of just 3 variables, del f by del x, or del f by del y, del f by del z. I'm sure you have seen such notations. And also del I. These are various notations that are used by various authors to denote the partial derivatives. Now, the partial derivatives are almost exactly the same concept as one variable differentiation. To compute the partial derivative at a point x1 to xn, you just fix all the variables. So suppose you want to compute let's say d1 of f at the point x. What you do is you just consider the map, you just consider f of so let me just erase this. To compute this, just consider t going to f of t x2 x3 dot xn, actually it should not be, consider f of x1 plus t. Consider the map f of x1 plus t, x2 dot 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 xn, where this x is equal to x1 to xn. So fix the values x1 to xn and substitute x1 plus t dot 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 xn into the expression. You will get a function of t, right? You will get a function of t. So this function of t, you just differentiate it with respect to t, just the way you would do if you are given a one variable function. Okay, so the derivative in this scenario is exactly the same as one variable differentiation. You just treat all the other variables as constant, just the variable that you're interested in, just plug in x1 plus t, get an expression of t and differentiate as usual. Okay, now what we have concluded is that if f is differentiable at x, all directional derivatives exist. All directional derivatives exist. That was the motivation before I defined the directional derivative, and in fact we have dv of fx is just dfx acting on the vector v. Okay, now the LHS, as you notice, is a number, and the RHS is a linear functional acting on v that will also give a number. So this actually makes sense. Now suppose we know that the RHS always exists, that is directional derivatives we are not assuming, sorry about that. Suppose we assume that the LHS, always exists, that is directional derivatives along all directions, suppose we assume that it exists, then does it mean that the RHS dfx, which is what we are interested in, does it mean that it exists? Well, let's think about this question for a moment. Notice that the right hand side allows you to give an expression for dfx. If we put the standard basis on Rn and the basis just set with 1. This is just one element, just set with 1 as a basis for R, then dfx in matrix representation, how do you find out the matrix representation of a linear map? Well, you act the linear map on the basis vectors and then just put the elements, the output vectors right down in the basis for the codomain and put them as the columns. So immediately you will see that the matrix representation is just d1fx, d2fx, dot dot dot, dnfx. This is a row matrix consisting of the partial derivatives. So what this is saying is, if f is differentiable, we have a nice expression d1fx, d2fx, dnfx. Okay, so this prompts the definition of the gradient, which is one of the central topics of this video. So definition, this is the definition of the gradient. Let f from u to r be a function such that all partial derivatives exist at x in u. We define the gradient nabla this is read nabla or just grad fx is by definition equal to this vector d1 fx comma d2 fx comma dot 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 dn fx. Okay, now rephrasing this expression in this slide that dvfx is dfxv, we can write that in terms of the gradient as well. So previously we have seen that dvfx is nothing but dfx v, but this expression that we have seen, dfx in its matrix form is just going to be the row matrix d1 fx dot 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 dn fx. So this is same as the gradient of fx dot product, the standard dot product, the standard inner product on Rn dot v. Okay, so we have several ways of writing down the directional derivative along v of the function f at x, provided f is differentiable. Now the natural question arises, suppose I know that partial derivatives exist at the point x, then does that mean that this d1 fx, d2 fx dot 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 dn fx, that row matrix, does that mean that this row matrix is nothing but the derivative of f at x? No. We have a counter example. Okay. Consider f of x to be equal to x plus y if either x equal to 0 or y equal to 0. Okay, and 1 otherwise. So this is a rather simple function of two variables. So this is a function f from R2 to R. Okay, now you can easily compute that d1 f of 0 equal to d2 f of 0 is equal to 0. Why is this the case? Because you will fix the second variable in the first case, second variable to be 0, so y is going to be 0, so the function f is 0. Now when you differentiate it, you are just going to differentiate the constant function 0, so you will get 0. Now let's compute d 1 comma 1 of f at 0. This just means taking the directional derivative along the vector 1 comma 1. Okay, so by definition this is just going to be limit f of x plus t 1 comma 1, or rather f of x y this is going to be f of x plus t comma y plus t minus f of xy by t, right? Why x plus t comma y plus t? Because the vector v we have taken is 1 comma 1. Of course the point we have taken is 0, so this just is nothing but I have to write limit t going to 0, of course. So this is limit t going to 0 of f of tt by t, because f of 0 0, when you substitute 0 comma 0 for xy is 0, this is just 1 by t, right? So the limit doesn't even exist, of course, limit t going to 0. So when you take the directional derivative along the direction 1 comma 1, then the directional derivative does not exist in this direction at x comma y equal to 0 comma 0. Okay, in fact the same argument shows, in fact, directional derivatives directional derivatives do not exist for any v1 comma v2 if both v1 and v2 are non-zero. If v1 comma v2 are both not zero, then that directional derivative along that vector is non-existent. The same argument will work. So what this shows is that partial derivatives can exist. Derivatives can exist without most directional derivatives existing. Okay, but from what we have seen, if the function f is differentiable, then all directional derivatives exist, right? So just the mere existence of partial derivatives do not guarantee that the gradient is going to give you the derivative by taking a dot product. Okay, you might think, okay, this is sad, but why do you assume only partial derivatives exist? So counter example 2 is going to say, even if you assume all partial derivatives exist, it need not be the case that f is differentiable. So again, consider f from R2 to R given by f of xy is equal to xy squared divided by x squared plus y power 4. This is when x is not equal to 0, and 0 when x equal to 0. Okay, now this function looks rather complicated, so I've just plotted this on Wolfram alpha, just the part xy squared plus x squared plus y power 4. I asked Wolfram alpha to plot it and it gave me something like this. As you can see from this picture, there seems to be some weirdness happening at the origin. It seems to be taking different values at the origin depending on which direction you approach from. So this picture sort of suggests that f is not even continuous at 0. Okay, so that's what we are going to be showing now. We are going to show that f is not continuous at 0, but nevertheless all directional derivatives exist. So f cannot be differentiable because a differentiable function is always continuous. Okay, so let's just first prove that all directional derivatives exist at the origin. So let v1 comma v2 be a vector such that so let this not be 0, such that v1 equal to 0, okay. Now you can immediately see that in this scenario dv f of 0 is nothing but 0. Okay, now if v1 is not 0, we can compute f of tv1 comma tv2 by t. This is what we want. This is going to give you the expression for the derivative, directional derivative at the origin in the direction v1 v2. When you substitute, you will get t cube v1 v2 divided by t cube into v1 squared plus t squared v2 power 4, which is nothing but v1 v2 divided by v1 squared plus v2 power 4. Okay, so this computation is valid whenever v1 is not 0. In fact, it's valid throughout, but the interesting case is when v1 is not equal to 0. If v2 is not equal to 0, it follows that this expression above, gives you dvfx, follows that dvfx is just this, right? And of course, if v2 is 0, just like the case before, dvf at 0 is just 0. So in fact, I could have just not complicated by taking v1 not equal to 0, v2 not equal to 0 and all that. First wrote down this expression and say that this expression is valid if both v1 and v2 are not 0, or if at least one of v1 or v2 is not 0. Okay, so the net upshot is, irrespective of my clumsiness, the net upshot is the directional derivatives at the origin exist. But f is not even continuous at 0. How do you see that? Well, consider the sequence Zn to be equal to yn squared comma yn and yn going to 0. So you are approaching the origin via this parabola yn squared comma yn. Okay, substituting in that expression for f, we will get yn power 4 divided by yn power 4 plus yn power 4, which is just half. Okay, so when you approach along this parabola yn squared comma yn, you get half, but f of 0 comma 0 is equal to 0 because we had defined f to be 0 whenever x is 0. Okay, so this shows that f is not continuous at the origin, and therefore f cannot be differentiable at the point x, at the point 0. Okay, so this shows that the directional derivatives existing, all directional derivatives existing, does not guarantee the existence of the derivative. Okay, now the reason for this is the following. All we know from the existence of the directional derivative is that along each direction the function behaves reasonably well because the derivative exists. However, the definition of differentiability requires the existence of a good linear approximation irrespective of the direction. Okay, so this linear approximation in some sense does not depend on the particular direction of approach. You have sort of a uniform expression that allows you to approximate the function f. So intuitively, the notion of the derivative existing is much stronger than good behavior in each direction, and this is captured in this example. Nevertheless, a minor twist can make the existence of the derivative guaranteed. What is that minor twist? You just have to assume that the partial derivatives not only exist, but they are continuous. Then it will turn out that f is differentiable. That is the content of the next theorem. Okay, suppose all partial derivatives of f exist and are continuous in U. Okay, so we are assuming all partial derivatives of f exist at all points of U, and the partial derivatives, that is these DIF, they are all continuous in U. Note, DIF would also be a function from U to R. Taking partial derivatives gives you back a function from U to R. Then f is differentiable in U. F is differentiable in U. Okay, the proof is rather nice. It involves a clever telescoping type thing. Proof. So fix x in U and let bxr be fully contained in U. Choose an open ball that is fully contained in U. Okay, now this ball I'm just going to call it B. Okay, just a moment, I made a slight error. So let bxr be in U and let b be be equal to B0R, not BXR. You will understand in a moment why I'm making this change. Okay. Now, if H is in B, then X plus H is an element of BXR which is contained in U. That's the reason why I defined this B this way, so that I'm guaranteed that X plus H is an element of BXR, which is in fact a subset of U. So X plus H is an element of U. So what do we want to investigate? We want to investigate f of x1 plus h1, x2 plus h2, comma dot 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 xn plus hn, and approximate it using some linear map, and of course I have to subtract f of x1 to xn. I have to approximate it by a linear map. Of course, x is x1 to xn, and h is h1 to hn. Okay, our goal is to get a nice approximation for this difference. Okay, now here is the trick. I'm going to write this difference as a telescoping sum. So that is why you would need actually that f is partial derivatives of f exist throughout U. In fact, you could have just assumed exist in some open set that contains x and get a local conclusion that f is differentiable at x, but I prefer to make this more what do you say, simpler statement, but less general. Okay, so what you do is you write this as f of x1 plus h1 comma xn plus hn minus f of x1 comma x2 plus h2 comma dot 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 xn plus hn. Okay, you have subtracted something, so you will have to add back something. So you add back the same thing, f of x1 comma f of x1 comma x2 plus h2 comma dot 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 xn plus hn. Okay, now subtract f of x1 x2 comma x3 plus h3 comma dot 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 xn plus hn. So you have subtracted one term, now you have to add it back again, so you keep going like this. Finally you will get f of x1 x2 dot 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 xn minus 1 comma xn plus hn minus f of x1 to xn. Okay, so we have just there is just going to be cancellation, so this term gets cancelled with this term will get cancelled with whatever term was supposed to be there within these dots. So finally you will be left only with this minus this. Okay, now what we are going to do is we apply the mean value theorem to each such pair. Okay, we apply the mean value theorem to each such pair, observing that in this difference only one variable is changing. So we can apply the mean value theorem. We apply the mean value theorem. We apply the mean value theorem to each pair. To conclude there is a point, or rather there is a number Ci in between xi and xi plus h. There is a number Ci in between xi and xi plus h such that this telescoping sum just becomes h1 d1f of c1 comma x2 plus h2 comma dot 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 xn plus hn plus h2 d2f x1 comma c2 comma dot 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 xn plus hn plus dot 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 finally hn dn of x1 x2 dot 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 xn minus 1 comma cn. Okay, I have applied the mean value theorem to each pair of equations here, and found out a ci in between xi and xi plus hi, such that I am applying the mean value theorem to that particular variable. So you get h1 d1 of f c1 comma x2 plus h2 dot 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 xn plus hn. Finally the last term hn dn x1 comma x2 comma dot 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 xn minus 1 cn. Okay, now what we want to do is we want to show that the derivative of f at x exists. So we need to construct an error term. So what we do is, because each one of these partial derivatives exist, we know that di of f of x1 comma dot 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 xi minus 1 comma ci comma dot 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 xn, each one of these partial derivatives, I can just write this as d1 of di of f of x1 dot 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 xn plus EIH, some error term. Okay, now why does this follow? Well, this you can always write down an error term like this, but what is key is that if such that E of h goes to 0 as h goes to 0. Okay, so let's look at this expression once more. What I'm saying is, each such partial derivative di f of x1 comma dot 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 xi minus 1 comma ci comma dot 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 xn is equal to the partial derivative at the point x1 to xn plus this error term ei of h, and this error term goes to 0 as h goes to 0. Well, this just follows because partial derivatives are assumed to be continuous in the hypothesis. We have assumed that each partial derivative is continuous, so there will be this error term, and this error term will go to 0 as h goes to 0. So net upshot of all this is f of x plus h minus f of x is nothing but summation I equals 1 to n, let me write the n properly, 1 to n hi di of fx plus hi ei of h. Okay, this just follows from this expression here. Each one of these partial derivatives, I have this further expression, I just substitute. So I get f of x plus h minus f of x is equal to summation I equals 1 to n hi di fx plus hi eih. Okay, but call this summation hi eih to be just e of h, define this to be just e of h, limit h going to 0, e of h is equal to 0, right? In fact, this is not enough to guarantee. What we want. We want limit. We want to consider limit h going to 0, e of h by norm h, right? So let's just take one term. Let's just take e1 of h by norm h. Okay, but we know that norm h would be greater than h1. So if you want to take the modulus, or rather the norm of this whole thing, no need to take the norm. This is just a real valued thing. Just take the modulus of this. This is going to be equal to. Or rather less than or equal to E1 of h, because modulus of h1 is less than or equal to norm h. Okay, so this just shows that a limit h going to 0 of E of h by norm h is equal to 0, because each term uh, E1 h by norm h1 E1 h by norm h, this one goes to 0. Okay, so we conclude that the error term that we have defined, E of h, has the property that limit h going to 0 E of h by norm h is equal to 0. Okay, this shows f is differentiable at x in u. Not only does this show that f is differentiable at x in u, we get the matrix representation of the map. It's just d1fx comma dot 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 dnfx. This is the expression for the derivative in terms of the standard ordered basis on Rn and the single vector 1 on R. With respect to this pair of bases, this is going to be the expression for the derivative. Why is this going to be the expression for the derivative? Well, because we have written f of x plus h minus f of x as summation I equals 1 to n hi di fx plus this error term, and this error term is sublinear. Okay, so this concludes the proof that whenever the partial derivatives exist and are continuous throughout an open set U, then the function f is in fact differentiable at U. Okay, so this allows us to compute derivatives explicitly using one variable calculus. Everything gets reduced to doing classical differentiation, which we are all experts at this point of time. So this concludes this video on directional derivatives and the gradient. In the next video, we will study some basic properties of the gradient and also interpret the gradient as giving the direction of maximum increase of the function. This is a course on real analysis, and you have just watched the video on directional derivatives and the gradient.